Now we're going to talk about the early days of computing, and this is where computer science and modern day computing starts. I want you to meet Alan Turing. In this field, you need to know who Alan Turing is. He is the founder of computer science and modern computing. In 1936, he came up with Turing's machine. Now, Turing machine, you need to know this machine. And we're going to be teaching just a quick overview of it here, and then go into more detail about it later on in another course. So during this time, David Hilbert came up with a challenge for the world, and he termed it a decision problem. What he asked the world was, could we take deductive human reasoning and absolutely express that in math such that it can be repeatable, reliable, consistent, and provable every time? Could you take a problem and definitively say it's true or it's false? Could you break steps down into that process? So Turing took on the challenge. And essentially he proved that not every problem is solvable to an absolute true or false. But what's interesting is that he used a proof which we term Turing machine. So let's walk through it. It has a CPU and it can do the following things. Now, before I get into it, I want you to picture in your mind a little robot, a little reading head, if you will, and an infinitely long tape. So on this tape, you divide it up into little squares. And within each square, it can have a state of the following: nothing. So nothing in that little block, a 0 written in that block, or a 1 written in that block. And then picture the little reading head sitting up above one of those little squares on this tape. Now, the little reading head can go right or left. It can move parallel to that tape. Okay, so you've got that picture in your brain. So the CPU could read the state on the tape. So it's sitting right above that little block, and it can read if that has a 1, 0, or nothing in there. That is data. It's pulling the data into the machine electronically, setting it up as a conditional state for the code. So if I'm sitting at block position on this tape, if I number them starting at 1 and all the way to infinity, so let's say I'm sitting at state position number 134. What Turing's machine would do is go and fetch the code for that particular state. So I read in, I know I'm sitting at this state position because I was told to go to that state position. So I'm sitting at 134, I go and I fetch the instructions or the code. I then read what's on that tape, and it gives me that conditional. I'm using the code, I can then decide if the conditional is set to a particular state. It may tell me, okay, I want to write back to the tape and change what's on that tape. Now think about that. We didn't have that before. So electronically, I can write. If it's sitting at a 0 right now, I can change it to a 1, or I can remove it completely and free up that memory on that tape. It can then tell it, okay, I've run through my little bitty sequence. I did an if, I want to write or change what's on the tape, and now I'm going to move to another position. And here's what gets interesting is I don't have to move just right or left one block. Instead, I can say, I want to move now to position 842. Or I want to move down to position 4. Or I want to move just one position, right or left, depending upon what the condition of what I read that state to be and what the code told me to do. It sounds like modern computing today, doesn't it? It also sounds like the beginning of a hard drive that I can read and write. I can pull that into a CPU like we have today. I can read a little bitty instruction, pull some data out, and do something with that data. And that process will continue until it gets a halt command, until it's done. So it can't be infinite. It has to be finite to be able to say at some point I've got to get done so I can solve this problem. So what I want you to take away from this is it has a read-write capability. So it's an early hard drive. It can handle data and code and subroutines. That's a biggie. I have the ability to start setting up my software, my code into libraries, which gives me that reusability, that subroutine and passing control to another position. So I'll move to a different position. I was at 134. Now I'm going to move down to 842, and I'm going to pass control when I get there to the state of 842, and it pulls down its logic. Okay, now I'm running this one, and I'm going to run that. That's a subroutine. It simulated modern day computing processes in our digital computer. And any problem that was solvable can be computed and run on a Turing machine, even today. So then, John von Neumann actually took Turing's concepts and developed it into an architecture. It had a CPU that could fetch data and code out of memory, just like we have today. It can execute the code, just like we have today. It can store the results, just like today. And it would continue until it got a halt command, just like today. Now, he called subroutines conditional control transfer. And those are the libraries and set us up for reuse. So what would that look like today? A subroutine in PHP would look potentially like this. It's a function, right? Or a method. It has a little block of code that can execute when it's called upon. It has an end statement to it. It says return. So it's not infinite. It can go through some series of code and then it returns out of there when it's done. And it's taking two inputs, right? It's got number 1, number 2, and it's taking those in and doing something with them. So it's reading that information. That information's been passed to it, and now I can work on it. So take a moment and look at this picture. This was the first all-programmable digital computer. It was back in 1942. This is Colossus. Now what I want you to see is all of the circuitry here. All the relays, there's tubes on there, there's various different digital components that are on this machine that if we were to look at it today, that machine is what gets scrunched down into our little computers and devices that we have now. Look at how much equipment and the size of the equipment that it took to do this machine. Now, it only did one purpose. The machines back then, even though they were all programmable, they served one purpose. This one was for decoding messages between Hitler and his generals. Now, some of the first machines that I worked on way back when in my career were relay logic. There were large panels just like this of relays that simulated what a computer could do. So a computer has little relays within inside of it, although they're little electronic circuits that can turn on and off through transistors and gates. This is actually using physical mechanical relays through wires. So you've got wires in here and it would turn on, it would get electricity on, off, 1, 0, and turn on the relay, turn off the relay. And then through contacts through that relay, it would go out, just like the light switch on your wall. So just think about, since 1943 to the little computer that's sitting on your desk right now, how that electronics got scrunched down in such a short period of time. Just imagine what we'll be able to do in another 10, 20, 50 years from now or longer. All right, so before we move on, I've got to introduce you to binary. Binary is how computers talk. Computers do not understand human readable. Instead, they understand little bits of electricity. So what we're going to do is I want you to get up and go walk over to the light switch on your wall. And I want you to turn the light on and off. So flip that switch up and down. So when it's in an on state, power flows from that switch, through that switch, to the light whether it's on your wall, on a lamp, on the ceiling, whatever, where your light is at, it will then turn on. Because power is flowing through the light switch that you just flipped, and it gets over to the light and turns it on. Now, when you turn that switch off, the light goes off. You just broke the circuit. So now power can't flow through that light switch anymore to get to the lamp. So that on state, when that lamp is on, is said to be a true state. And the digital value for that is a 1. The off state, when that lamp is off and that circuit is broken, is an off state. That's a 0, digital 0, or a false condition. You need to remember this. This is very important. So make sure you're taking notes right now. Now look at the electrical circuit that's just below the images that you see there. All right, so we're going to deal with the on state first. When the switch is in an on state, the circuit is closed, which means power can flow through that switch and get to the light. See how it's got a continuous wire there that can flow through. Now move over to the off state. When you turn that switch off, notice how the switch arm actually opened up. I have an open circuit now. I've broken the circuit. Power can no longer flow through there because that little switch is now open. If you need help thinking about it, think about a drawbridge if you've seen a drawbridge, where you pull up, you're in your car, you're walking, you're on a bike, you're sitting at a bridge that's going over a river, and a boat's going to come through, and they raise up the bridge. You can't drive through or walk through. That road is no longer open to you. So traffic cannot flow through there until they put that bridge back down again. And once they do, now traffic can continue. It's the same way with electricity. That switch works the same way. When it's down or closed, power can flow through, and that's an on state. That's a 1. When that switch is open, power cannot flow through, so that's an off state. The switch is 0. Let me give you one more example to help you understand. Think about water. Walk into your kitchen and turn on your faucet. What happens? Water flows through, right? That's the same thing as power. When I close that switch, when I turn on my lamp, what's happening is the water or the power is flowing through that wire. So if you can think about the wires being like conduits, little pipes holding the water that flows through. So if you think about those little pipes, you turn on your faucet in your kitchen and the water flows through the pipe and it flows through the faucet and goes into your sink. And when you turn it off, an off state, what happens? The water stops flowing, right? That's right. So that is an off state. You've broken the circuit. You inhibited the water from flowing anymore. And that's what we're doing here with power. And that's how power works. That's how electricity works. That's how electrons flow. We're going to get more into helping you to understand electrical circuits and binary in a future course. But for now, I just want you to understand the on is 1, the off is 0. So binary code is comprised of 1s and 0s. A bit, one single bit, is either a 1 or a 0. Okay? So now we know what a bit is. A single 1 or 0. What's a byte? You hear about bytes all the time. We know that there are megabytes, gigabytes, terabytes, kilobytes. What's a byte consist of? A byte is equivalent to 8 bits. So if you take those 1 or 0 pattern and you take 8 of those in any combination, you'll end up with a byte. So for example, here's a pattern that I'm showing you here. Notice that the first 4 bits are just 0. And then there's a 1, 0, 1, 0. This particular pattern is going to be equivalent to a decimal 10. Now, I don't want you to get stuck right here. Don't try to worry right now about how do you convert a decimal 10 into binary. We're going to go over that later. Matter of fact, in the next course, we're going to go into understanding binary, converting from decimal to binary, decimal to octal, decimal to hexadecimal. So for right now, I just want you to know that there's a pattern here. Computers only understand ones and zeros. That's it. That's all they understand. So if a 1 or a 0 is equivalent to a single bit, putting 8 of those together gives you a byte. Computers do not understand this. This is human readable code. So in your code, if you have $result equals number 1 plus number 2, computers don't understand that. They only understand ones and zeros, and that's it. So that's what I want you to know here. I introduced you to a little bit of electrical circuitry so that you could understand how an on state is a 1 and off state is a 0, how that breaks down into what the computer understands. So that little bit of electricity of no power flow is a 0, and when there is electricity, it's a 1 or 0. That becomes binary code. Again, we're going to cover that in the next course. So to help you understand, it's very important that you understand what your code is doing. So we're going to do something very simple. We're going to add two numbers together. So if I have A equals B plus C, or like I just gave you in PHP, if I had $result equals number 1 plus number 2, we broke that down and just said, okay, let's just do a mathematical expression of A equals B plus C. And these are variables. Whatever language it's in, they represent actual data. All right. Machine code is the code that runs the ones and zeros. That combination of patterns of binary code is what drives your CPU and your computer. So when you have an expression A equals B plus C, you would think it just adds that together, right? It seems like a simple instruction, but it's not. It actually takes 4 separate steps. Machines are not smart. They're extremely efficient, but they need to be told exactly what to do. So let me walk you through the thought process. This is just a thought experiment. The very first thing it has to do is load B into working memory. Now, I'm going to show you the binary, the machine code. I don't want you to get lost in the minutia of what does this code mean? That's not the point here. The point here is just to give you an appreciation of how A equals B plus C gets broken down into the ones and zeros that go into the computer. That's it. So don't get lost here. Stay with me. To load B into working memory, the CPU needs to see a set of commands, a pattern of ones and zeros. This would be an example to show you that particular pattern. So the very first 4 bits that you see is going to signify to the CPU, it knows to look for this particular pattern. If it receives this pattern of ones and zeros, it says, okay, this is a load instruction. Therefore, the rest of the bits need to be laid out in a particular pattern to support what this load instruction is. So it's broken up again into another series of bits. And the second one is going to say, all right, this is the register where we need to put B into. So this is the working memory. It needs to be the register's address. So that's what that is. That's an address. And if you go to the last 4 bits, you would say, okay, this is the address of where B is currently stored in memory. We're going to tell the CPU, we're going to do a load, and you're going to pull it from that storage location, that address, which here we have as decimal 1. Again, don't get lost on the conversion from decimal 1 to binary. And we're going to put it into the working memory, the register address, which we're saying here is decimal 11. All right, what's the next step that we need to do? Next, we need to tell the CPU that we've got to load C into working memory. Now, do you see when you're looking at this, A equals B plus C? The very first things that we need to do is tell the CPU what? You got to go and pull the values, that data from where B and C are, you've got to pull those into an area where the CPU can start to work on them. So they're sitting off in storage somewhere. We've got to pull them into working memory, which are these registers. Okay, so we just did B. Here's C. Again, you see there's a load pattern. And it says, all right, this is a load instruction. And I want you to take C, which is that last 4 bits, where it says 0002, which is a decimal 2, by the way. You're going to take that out of storage location 2, which is where C is sitting at right now in memory. And you're going to move that into working memory, which is register 12. 12 is represented in binary as 1100. So you see the pattern. It's a pattern of ones and zeros. That's what I want you to get from this. You're seeing a pattern of ones and zeros. You're seeing that, oh gosh, there's a lot of steps here. It's not just A equals B plus C, right? The CPU needs to be able to pull these into memory to do something with it. So what's the next step? Now we've got it sitting in the CPU. We're ready to start our operation. Now it's time to add them together. So we're going to add B and C. We know that B is sitting now in register 11 in the CPU. C is sitting where? Register 12. I hope that's what you said. Register 12. So that's what we're going to do. We're going to add together register 11 and 12, and we're going to put that into a result register. We're going to put that into register 13. All right, so let's take a look at what we have here. The very first 4 bits are what? They're the instruction. So this particular pattern, which is 1011, again, this is arbitrary. But let's say 1011 is an add instruction. So the CPU sees, okay, that's an add instruction. Now I know what to do. The next 4 bits, I know, okay, that is where I need to put the result of this add. And I'm saying that that is register 13. The third and the fourth series of bits is where I'm pulling the data from. Within my, if my being the CPU, within my working memory, which are my registers. So I take register 11, I take register 12, I add them together, and then I put the result into register 13. That's my add instruction. Then I'm going to come down and I'm going to do what now? I've got the result sitting within the CPU, but now I've got to store it away. I've got to get it back and store it away for permanent memory, because as you'll learn later on in the next course, what's in the CPU is just there for that operation. So then it pulls in the next operation and it's ready to start again. So we need to store away that data. All right, so I need to store the result. It goes in and it says, okay, this series of bits, my first instruction, my first 4 bits, and here I'm showing it as a 1100. Let's say that equals a store. And just like you saw from the other patterns, first I need to tell it where do I want to store it at in memory. So here we're going to say we're going to store it in decimal 3. Okay, where in the CPU's registers, where is that result at right now? What's the address of that register? And you see if you go back up to step 3, what's the address of the register for the result? 1101. That's a decimal 13. As you look at this, what do you see? What do you see? Would you like to take A equals B plus C and walk through each one of these steps down at the machine level? That would be pretty cumbersome, wouldn't it? So I want you to just get an appreciation here. That's what I'm trying to get you to see, is that A equals B plus C down at the very basic level of your computer, at the CPU level for the machine code. Here's what's going on. Step by step by step. There's a lot of steps to this, aren't there? Imagine doing your code right here at this level. How cumbersome that would be. How arduous it would be. How error prone that would be versus just writing A equals B plus C. So what are your takeaways from all of this? A Turing machine is the basis of modern computing and digital computers. Alan Turing is the founder of computer science and modern-day computing. Our very first all-programmable machine, albeit that it did just one single purpose, was what? It was Colossus. Computers understand ones and zeros, not human-readable code. And machine code is specific patterns of binary code. And of course, we just showed this, that if you had to code all day long, hour after hour, imagine creating a website and down here in machine code, ones and zeros. Boy, it wouldn't be much fun, would it? It's arduous and it's not fun. However, the whole purpose of this was to show you how your code breaks down all the way down to the computer level. And we're going to take a look at that in the next course.